Hi everyone, Dave here. This is obviously lecture 5. We're going to be talking about covalent molecules, etc., as you can see from the first slide there. Before I start in this lecture proper, I just want to refresh your memory on a few things. I'm just going to grab my pen here. Now, if you recall so far, we've been talking about the idea that things always react to look like their nearest neighbour noble gas. And one of the strategies for doing that is when you have this sort of arrangement where you have sodium and chlorine. Sodium needs to get rid of an electron, and it does so and gives it up to chlorine that needs to take one. They need to do that, of course, because then they'll look like their nearest neighbour noble gases. So the strategy is give and take. The goal of the game, of course, is to end up looking like your nearest neighbour noble gas. Now, there is another strategy for looking like your nearest neighbour noble gas, and it's not this give and take arrangement here, but it's actually a sharing arrangement. So let me illustrate that by example. If I draw hydrogen here, we all know it's got one electron, so there it is there. I draw another hydrogen, we know it's got one electron. Now I'm going to indicate the two different electrons belonging to each of the two atoms by drawing a circle with one and a cross for the other, but that cross is an electron. Now the way in which these guys can actually gain something like a nearest neighbour gas configuration is if they end up with a sharing arrangement. So if you look at this hydrogen here, from its standpoint, if it can kind of have that other electron for some of the time, it's then got two electrons, and it looks like helium, which is really good for it. It's looking like its nearest neighbour noble gas. And then the same argument's going to apply to this hydrogen here. It's going to look like its nearest neighbour noble gas. That is, it's kind of got those two electrons there. Now, it's probably not as good as this give-take arrangement that you've got with sodium and chlorine here, where sodium gives an electron and chlorine takes one up. It's kind of like a marriage made in heaven, if you like. But in this one here, at least for some of the time, both of those hydrogens have got that nearest neighbour noble gas configuration. Now that arrangement, where that happens there, it's a sharing arrangement. It's referred to as a covalent, that is, sharing bond between those electrons there. So I can, or between those atoms there, I should say. So I can draw that kind of arrangement. In another way, I can put a hydrogen here, a line, and then another hydrogen. Now the line is just simply meaning that they're both sharing an electron pair. And together, they've got that nearest neighbour gas electron configuration. So that's part of what I'm going to be talking about today. And also some other pretty cool and interesting things as well. You can obviously read those learning objectives at your leisure some other time. Skip through those. Okay, so I've already made my first point there, what the nature of a covalent bond is and why, and how you would represent it, and that is by a single line. There's an example there, boron trifluoride. So I'll just flesh this out a little bit more with this molecule as well. This boron here, if you look at the periodic table, it needs 3 electrons to look like its nearest neighbour its nearest neighbour noble gas, which is neon. And it does so by then engaging in a sharing arrangement with these fluorines, and in a sense it's picking up, at least for part of the time, an electron from both of those fluorines. Fluorine only needs 1 electron, and it'll pick that up by having a sharing arrangement, each fluorine, with this boron here. And by that method, all 3 of them are engaging in a strategy which is allowing them to look, at least for part of the time, like their nearest neighbour noble gas, at least as far as their electron configuration goes. I'll just point out to you that there's also double and triple bonds that occur with these sorts of arrangement, these covalent arrangements. So an example of that is these guys here. So we've got ethene, we've got 2 carbons here. both of these are sharing 4 electrons in total. Remember, each one of these lines represents 2 electrons. So if you look at this carbon here, it needs 4 electrons to look like its nearest neighbour noble gas. It's picking up 1 from this hydrogen, 1 from this hydrogen, 2 from this carbon, and 2 from this carbon, making your total of 8. So it's got that electron configuration of neon. And the same for this carbon here, of course. In this one here, we've got ethyne. It's got, well, if we look at this carbon here, it's picking up 1 electron from this hydrogen, at least for part of the time in this sharing arrangement, plus 3 from this other carbon here, making a total of 4 that it's picking up, in a sense, making a total of 8, making that nearest neighbour noble gas configuration, that is neon. And just point out to you too that often when you're drawing these things, you don't put in the non-bonding electrons. So for example, in fluorine here, if you look it up, you'll realise that fluorine's got 3 pairs of electrons here that aren't involved in bonding, and you often don't put them in the dots. Sometimes you do, but sometimes you don't. The last thing the last point I want to make about this slide is this word here, molecule, because I've avoided using it before, and it means something special. What it means is an arrangement where you have this discrete unit of atoms and that they're joined together by covalent bonds. So ionic compounds don't form molecules, they form that lattice structure I was talking about, but non-metallic compounds form covalent bonds which then form molecules. And so you can see they're very different things indeed. Right, I just we need now to have a look at this term here, electronegativity. What it is, it's a measure of how much atoms pull electrons when they're involved in covalent bonds. Because you can imagine that not all, when they're involved in these covalent bonds, atoms not always share electrons equally. In fact, some atoms are much better at pulling electrons towards themselves than others. And this measure of pulling power is called electronegativity. You should realise that non-metals tend to have higher electronegativities than metals. That is, the things on the right-hand side of the periodic table tend to pull electrons more. And I'll illustrate this point here by actually showing you this periodic table. So here we have a periodic table showing how electronegativity changes. These numbers are the electronegativities of the respective elements. The higher the number, the higher the electronegativity, or the higher the pulling power. So as you go across the table here, electronegativity tends to increase, and as you go down the table, electronegativity tends to decrease. Now you might ask why that is. Well, there's a perfectly logical explanation for that. And that is, as you go across the table here, what you're doing is adding electrons in, but they're not actually any further away from the nucleus. They're staying at more or less the same distance. And as you're adding electrons in, of course, the atomic number's going up. That is the number of protons in the nucleus. So the magnitude of the positive charge in the nucleus is going up. So there's a greater pull on electrons. So it's not surprising that as you go across the periodic table here, the grip on the electrons becomes more and more. As you go down the periodic table, as you well know, you're actually increasing your principal quantum number or shell number, and that means that those electrons are moving further and further away from the nucleus. So the grip that the nucleus has on those electrons gets less and less. All this culminates in this element here being the most electronegative in the periodic table. That's fluorine, so it has a value of 4. I'll just point out to you too that these 3 elements, nitrogen, oxygen and fluorine, are in fact the 3 most electronegative in the periodic table, and that's something to keep in mind for something else I'm going to discuss in a moment.